So we're ready to get started. I wanted all of the judges to just give a really quick introduction, like name, something about you, so that all of the participants know that you are a judge and who you are. So if the judges could just unmute themselves really fast. Thomas, if you want to start off, and then Hannah,
Yeah.
and then Dr. Choi, and then Anthony, if you want to go last.
Sure.
So, hi, I'm Thomas. I was the B Hours program manager before Liz. I've been doing design for like the past 8 years, so I know a little bit about that. I've done the Makeathon a little bit, so design's kind of where I've gone with my career.
Yeah, and hi, my name is Hannah. I am a 2018 BME graduate from UC Davis. I am currently at Abbott Structural Heart, and I'm working as a supplier quality engineer.
Dr.
All
Choi.
right. Hey guys. Yeah, I'm Jennifer Choi, and I don't know, what should I say? I feel like, do I know most of you guys? I'm currently teaching senior design. Probably saw many of you in BIM 1, maybe BIM 20, and I'm excited to be here.
My turn.
Yep.
Hi guys, this is Anthony McLennan. I'm a graduate from UC Davis. I got my master's and my undergraduate done at UC Davis back in, I think I finished off in 2010. I've been working for HP Labs in Palo Alto for the last 9.5 years, all doing research engineering, most recently in our additive manufacturing lab. And my career has been driven more towards a marketing function, giving tours and demos of our technology to customers.
Okay, so just so that everyone knows what the plan is, each team's going to go and present their design or designs. I think there's one team that has 2 designs that they wanted to present. And then after they present their design, there'll be a period for judges and other team members to ask the team that just presented questions about their design or give them feedback, provide commentary. Very similar to like if you've done the Makeathon, how that works, where you present and then there's a question period, and then we'll move on to the next team. And once all of the teams have presented and received feedback, all of the team members can log off, and there'll be a period of deliberation with the judges who are here. And then I'm going to send this recording out to the judges who couldn't be here live, and they will deliberate with the rubric that I've provided. And then I'll tally everything up, and you should know the results by Monday at the latest, hopefully. Sound good? Head nods? Sweet. Okay. So team 3, if you want to take it away. Team 2. You should have sharing permissions. My bad. Team 2 wanted to go first. So team 2, if you want to share your screen, you should just be able to share over. Sweet. Okay. Go
Can you hear me?
Mm-hmm.
Okay. So our design is auto sterilizing glove. I'm Samveda.
I'm Adit.
I'm Kimberly. Nice to meet you. Okay, so the problem that we were addressing with our glove is that there's been a shortage of protective gloves for healthcare workers recently, mainly because the common population has been using up a large amount. So with our product, we're hoping to diminish the amount of gloves that are being used. So if we took a look at current gloves, they're mainly single use, and you have to change them after a couple of hours. And the worst thing is they can't kill viruses. And though they may keep you from contaminating yourself, they pose a risk for cross-contamination.
So our solution is a self-disinfecting glove, which will disinfect the surface of the glove and other surfaces that it touches. And basically, it will also help prevent cross-contamination. And so our glove has like 3 layers. The first layer is to protect your skin. The second layer has the absorbency layer, which will contain the solution. And then the third layer is the top layer, which will have pores that will help help seep out the solution?
So really quick on the materials of the glove. The glove itself will be made out of nitrile, which you are all probably very familiar with. Nitrile is the material used for the gloves for chemistry labs here at UC Davis. And then the absorbency layer itself will primarily be made out of cotton, and it will be preloaded with some disinfecting solution.
So how it works, it's basically, our glove is based around the concept of tactile pressure. Which is similar to how a sponge works. So basically when you go to grab or touch something with your gloved hand, the tactile pressure from grabbing or touching that surface or object will release the disinfectant solution from the glove through the pores that you saw on the outer layer on our diagram. And the release of the solution will kill any viruses that might have come in contact with the glove surface, as well as those that exist on the surface or object that you touched. So for example, if you're out shopping and under normal circumstances, if you're wearing a regular glove that most people are right now, if you were to touch, for example, like a guardrail that has the virus on it, it won't get on your hand, but that virus will stick to your glove and it'll stay there. So when you move around and you touch other things, all the objects you touch after that guardrail will also now be contaminated. But with our glove, when you touch that initial contaminated surface, the virus will die on the glove, which means you won't continue to spread it around, and it'll also clean the spot on the guardrail which you touched. So which is just an added benefit. And after using it, after you come back home from shopping, you can take off the glove and place it in an airtight container, kind of how we see disinfectant wipes today. And that box will come with the gloves themselves, and that box will preserve the disinfectant and prevent the solution from drying out, so you can go and use it again later.
So we were able to do 2 prototypes. This is the first one. And the picture on the left shows that we use pads to mimic absorbency layers because they are pretty great materials. And so as you can see, image on the left is we cut up the pads to mimic the hand shape. On the image on the right will show that it's attached or like glued on to the first layer. The first layer is a white glove. And then the second layer will be the blue layer, which has the pores in it. This is there's 2 methods which you can use the glove, and this method also uses tactile pressure. So you make a fist, and then as you can see, image on the right, the solution comes out, and then you can go ahead and touch other surfaces. This is method 2. It also uses tactile pressure. Simply just touch any surface you want, and because of tactile pressure, the solution will come out. And as you can see, the image on the right here, the solution's getting transferred. This is our second prototype. I think provides a better visualization. Here, I used pads again, but I also used a green color solution so you can see better. The purple layer is the first layer. This is our absorbency layer. This blue layer has the pores in it and will go on top of this layer. So this is how it should look. And then this is another demonstration that we did. So let's say you go grab a bottle, right? And you're wearing our glove, and our glove has a solution in it, and then you touch it, the solution will get transferred, it will disinfect this object, and it will disinfect your glove.
So the chemical solution that we thought would be suited best for our product is called CleanSide germicidal detergent. It's a citric acid-based solution, which are amongst the safest options for disinfectants. And it provides a high effectiveness against COVID-19 and many other viruses and bacteria. The EPA has actually formally listed it as a solution to use against COVID-19. Another benefit to this solution in particular is that it's minimally corrosive, which will protect the material of our glove and stop it as much as it can from burning through the layers and making the glove less effective. Oh, and one more thing. CleanSide, it also offers a benefit that it's fast working compared to some other solutions. It has a dwell time of 5 minutes. And if you don't know, dwell time is the amount of time that the solution needs to stay wet on a surface for it to be effective. So yeah, CleanSide has a dwell time of 5 minutes compared to 10 minutes and 15, even 15 minutes for some other solutions.
Okay, so some issues that we need to work out is definitely how the glove itself, the material of the glove will be affected being around the CleanSide solution for so long. Even though the CleanSide solution is relatively non-corrosive, it's a pretty mild solution in terms of that. The glove material itself will eventually start absorbing the solution itself, but because it also has the absorbency layer will also be absorbing the solution. So we really need to do some testing to see how to keep the glove, or just to see the glove's rate of deterioration with the solution. And also another thing we can find out is determining the optimal amount of absorbency solution, like the thickness for it to be, and also the amount of solution itself to be in the glove at one time.
Okay, I think that's about it for the presentation.
Okay, that was awesome. So now's a period of questions and feedback. Thank you for the slide. So if judges have any questions or feedback, or if other teams have any questions or feedback, now would be the time.
All right, I guess I'll start. So my first concern is because you have a lot of moisture on the outside, and that is the purpose of your device. Do you have any concern about how tactile it will be once it has a solution on it? Like, will it still be like fit and snug to your hand, or will it like conform because of all the extra padding that you put in it, if that makes sense? Like, will it still allow you to operate with the correct amount of finesse that you normally have with a normal glove?
So I think that you will, so when I put it on, I was still able to, I had kept it on my hand for a pretty long time, and I was still able to function pretty well because the first layer was on pretty tight. And even though the outside layer had, like, as you said, it had the pads and stuff, and it was like complete, but it was not a big issue because I still had the first layer on the glove, and you can also dry it up, like if you wanted to, like if you no longer wanted it to be wet, just like dry it off and just don't yeah, it can stay dry if you wanted it to. If you want a lot of liquid to come out, then you make the fist. That's what the method is used for if you want a lot of it. But if you want just a little bit, then you can just normally touch the pressure. So there's ways to control how much you want. And if you dry it up, it will stay dry until you again release more solution.
And then my other question was, is this more intended for like civilian use or more hospital?
I think we did mention it. If we didn't, it's meant for like grocery workers or like delivery people, not medical workers, obviously, but so that this people can use this glove and not the actual gloves that like doctors need, and it will, I guess, create more PPE gloves.
Awesome, thank you.
So I'll jump in. This is Anthony McLennan. I love the prototypes. Just starting off, I was kind of curious what you guys learned from Rev 1 to Rev 2. I also had a question on your cost estimation, and then your design intent for how long you would use the glove, or how often the person would be able to use the glove. Would they take it on? Would they be able to put back on? Is it single time use? Is it designed to use for 4 contacts, 5, an hour, et cetera, et cetera?
Okay, so to answer what we learned from prototype 1 to prototype 2, prototype 1, when I made it, I first originally put it on a tissue paper just because I was playing with the idea. And then I realized because I had like didn't directly like glue it onto the glove, it kind of crumpled up when I put on the second layer, and it was also hard to put on the top layer of the glove. And so when I made the prototype 2, I used tape to kind of securely tape it on the hand. I think I'm gonna go back and show you it. So this over here, like it's more secure over here. And I think what this did was that it made the overall thickness of the glove, like it was pretty thin compared to prototype 1. So it's another benefit because it wasn't bulky in this way. So that's what we learned, that there's ways we can make it less bulky, more like productive, I think, if that makes sense. And then I think your second question was how long, like what is the lifetime of this? So we're hoping that it's gonna last more than like what we need. Like normal gloves are, you know, like 2 hours and then you have to change it. So we're hoping that this glove lasts longer than that. And we won't know much because we have to experiment it. But some ways that we can prevent, some ways that we're thinking that we can use to make it last longer is the airtight container that we talked about at the beginning of the slide. So after you use it, and let's say you don't, like you're not gonna use it. So you take it out and you put it in that airtight container so that the solution won't evaporate. And I guess you can keep using it until the solution evaporates. We probably need to do more testing to figure out that, but we're hoping it lasts like 6 hours, 8 hours. That's what we are kind of estimating. And I think my partner will answer
just to add on to that, our main goal is just to make it more than a single time use like current gloves are. So that's really the goal, but we anticipate with the amount of solution that we planned for in our report that we included, we hope that it lasts at least a day's worth of use. And yeah, we will need to experiment more with the actual solution itself since we don't have it on us right now, just to see how long it stays in the glove and how much will come out with each touch. But yeah, and as far as cost goes, it was a little bit hard to gauge. So we calculated the cost to be about $2 per pair of gloves for cost of production. But I do think that that price is pretty inflated right now because of the shortage of disinfecting solutions on the market right now. Like they're very overpriced, obviously because there's a low supply. But that's just from my research looking at commercial websites. So we're hoping at least that when we buy in bulk, if this were to go in production, that the price would be much cheaper.
And then kind of going off that question. Oh, sorry. Go ahead, Dr. Joy.
That's okay.
Oh, okay.
Are you sure?
Yeah.
Okay. All right. Well, I just want to say really nice job and really nice efforts in prototyping and testing this idea. So I guess I'm just wondering if you've thought about final materials that you could use for especially that layer to hold the solution.
Okay, so we were mainly looking, what do you mean the layer, like the absorbency layer itself? Okay, we were mainly looking at what pads are composed of, and they're mainly, at least from the ones that we were looking at, they were mainly composed of a regular cotton layer and then a more in-depth absorbency, like more absorbent layer. If that makes any sense?
Yeah, it's from like wood cellulose.
Yeah, so we were looking at that, but obviously pads are meant to hold onto blood and our absorbency layer is holding onto a solution. So we would also need to test how the cellulose layer would react to that. Cotton itself would probably not react negatively to it because it's just cotton. And then of course, we were also thinking about what kind of glue to use on the absorbency layer to attach it to the glove itself. And we were looking at epoxy glues, which we were thinking would be more chemically resistant and not become dissolved in the solution itself.
I think the glove would be used to stick the pad or the absorbency layer to the glove. I think that's what we would use a glue for.
Yes.
Got it. Awesome. Thank you.
Hey guys, I have a question. First, I want to say nice job on the prototype. That's pretty cool, and I have yeah, it's obviously very prevalent right now with grocery workers and everything that we're hearing in the news. I was wondering, did you guys think about manufacturability and how, say, if this were to go to industry, how you would try to manufacture this?
So we actually included in the report that we wrote, but I think we didn't do it in the slide. I think because the way I made it was just using one glove, attaching in and using other glove. The process is similar to just like manufacture gloves. And then I think there will be an extra added step to attach the absorbency layer. And then we're thinking that the absorbency layer will come pre-filled. So if it's, let's say there's a manufacturing line and there's like gloves being made. So before, I guess, because I know that there's like molds made where they, I guess, dip it in like liquid, or like it's like liquid latex.
Liquid rubber, yeah.
Yeah, liquid rubber. And then, so it's like on a mold. So they have to remove the glove out. So before they remove the glove out from the mold, they'll probably attach this absorbency layer when it's on the mold. And then they'll, I guess, add another glove layer. And then I think I forgot to mention this, but another thing is that, as you can see over here, it's important that you seal both of the layers. So that's what they'll also do at the manufacturing line. That this is the first layer, this is the top layer, and then I basically just rolled the cuff over so that the liquid wouldn't seep down.
Yeah.
And so I think that will also be done during the manufacturing line. And so I think it will be made normally how gloves are made, but just few extra steps.
Okay, that makes sense.
Yeah.
And then one other quick question I just thought of. Did you guys think about how is this going to fit different size people with different size hands?
We did. So I think, again, it would also, this works in the manufacturing to, like, if you're making medium-sized gloves, like you would make different types of gloves, right? You make different types of base gloves, and then you would add the absorbency layers, and then you would add the same size glove. So it can work for different sizes too.
Okay, that makes sense. Thanks for explaining.
Any final questions before we move on to team 3? We good?
No. Good job, guys. That was
Yeah,
great.
that's cool.
Yeah,
Thank
cool
you.
idea.
Thank you.
Okay, team
Okay.
3, do you want to share your screen?
Is that us?
Yes.
Give me a second. Sorry. Yay.
Cool, I guess I'll start now. Hello, my name is Joshua, and our team decided to do the COVID project on the bubble room.
Okay.
Next slide, please. So what is it? So we wanted to find a way to contain the COVID virus in a sanitary manner, and that's exactly what the bubble room does. It's basically a pop-up tent that works to contain the virus, and it utilizes negative pressure to keep the patient that's inside of it contained without spreading the virus particles to outside and infecting other people. It helps to create extra room in hospitals when the healthcare systems are overwhelmed, just like it's been in the last few months because of this pandemic. Next slide. So some unique features that we had was that it was easy to set up. It's portable. It can move very easily. We decided to put water in the hollow walls so that it would be stationary when it would be outside, or if it had to be outside because of the hospital being too crowded. It also gives hospitals more room, so they're not under the stress of having crowded hallways. It utilizes negative pressure, which will be explained later on, and also uses high density polyethylene sheet, which will also be a part of our material list, which will be presented.
Our bubble room consists of one main room, and this room houses the patient and also all the medical equipment that's needed. Its dimensions are 480 by 320 by 320 centimeters, and in total it's 165 feet squared. The water will be used to fill some of the panels, and this helps to keep the structure weighed down. And in total, the amount of water is 110,955 centimeters.
So with the materials chosen, we chose high density polyethylene sheet. Oh, Ali, can you, do you mind if I screen share the CAD real quick?
Um,
Can you guys see my screen?
Mhm.
All right, so here's our CAD that we made from the bubble idea. So this is our bubble, our portable room that we've been talking about. Inside is an airtight sort of room that a patient can get into and be housed in case there is a room shortage. And the thing is that, see these panels can be folded in, like can be folded in to be a small square. These units out here, they're an input and an output machine. So with this input machine, it takes out air from the room and runs it through a filter. And with the other one, it takes an air in and puts in air. And these machines are specialized to create a negative pressure effect, which we'll explain later. Also with these rooms, you need to have power to allow like ventilators and other devices to be inside. So here we have outlet right here. And there it can connect to extension cables, which can extend to actual other powers, which is outside the room. And right here is where the entrance would be in. Like you can share your screen again.
Yep. Okay. Give me a second. Okay.
So with the materials that we chose high density polyethylene sheet. Now it is non-porous and non-stretching. What non-porous means is that air can't seep in and seep out. It also is UV resistant, so the elements won't be able to go in through. They're going to be used for the panels, like I've said. And then for the sheet that allows the patient to, or that extends and allows the patient to, that makes up most of the room, is the linear low density polyethylene. In the CAD, it was clear, but however, it can also be opaque if the patient wants to have more privacy. It's also non-porous as well, so nothing can see through it. It's stretchable and it's tear and puncture resistant, so that way the elements can't get through. So on the bottom, you can see the dimensions and the calculation it costs to produce each part. So it would come out to a total of 9,800 for the parts for the materials alone. And you can move on to the next slide. And here you can see what types of materials are used and what examples they use for. So the manufacture methods is, since they are plastics, they are pretty cheap to make. So what we're gonna use is a process called fusion welding. And there are two types of materials that come from the United States Plastic Corporations, which sells high density polyethylene and linear low density polyethylene in sheets.
Okay, so we're going to be using negative pressure to ensure that COVID-19 particles cannot escape the room. And what negative pressure essentially means is, as you saw in the CAD, we had those two machines that exhaust and supply air into the room. And we're going to specifically affect the rate so that the more air is being pushed out of the room than is coming in. The exhaust will be faster than the supply. And what this essentially does is that the pressure inside the bubble room will be less relative to the outside. And what this does is, because, like, in order to equalize the pressure, air will be forced to rush in to our negative pressure room under the cracks of the door. And this is really advantageous because since air is only able to go in, air cannot escape. That way, the COVID-19 infectious particles cannot escape the room. And we're going to use this to our advantage. And so these are the specific machines that we chose to do this job. So on the left, this is the negative pressure machine. And this has a HEPA filter built in so that when we're exhausting air to the outside, it does not have COVID-19 particles in it that can infect everyone. And this is the supply machine, and this also has a HEPA filter because we wanted to be able to expand the bubble room to potentially other applications, which will be explained in the next slide or one of the next slides.
And these are the specific numbers based on the dimensions of the room and CDC requirements based on, you know, like air changes per hours, etc. I'm not going to go into the details of this right now.
So there are some alternative applications, like Alik mentioned. For example, even though this room is designed for negative pressure, we can also turn it into a positive pressure room, which is essentially the opposite. Instead of keeping all the bad particles inside the room, a positive pressure room keeps all the bad particles out by making it so that more air is supplied rather than exhausted. So this is really helpful for like immunocompromised or immunodeficient patients, for example. And if you go to the next slide, you can see a little video of how it works. You can see the air coming in through the vents, and then it's exhausted out. And yeah, that's it. Thanks for listening.
Okay, thank you. Any feedback or questions?
Yeah, this is Anthony. I'll jump in again. I was hoping you can go back to the design prototype. I had a question on functionality.
The CAD?
Oh, yeah, let me.
Yeah, what you guys imagine the product to actually look like.
All right.
So can you remind me what the height is?
The height, it is, you have a dimension sheet. Height is going to be, sorry that we didn't mention it. The height is going to be 300, oh no, sorry. The height will be 3,222.62 millimeters, or I don't want to do conversions. Sorry about this.
320 centimeters, Josh.
Yeah.
Yeah.
And then how big is the door?
The doorway, we haven't catted out right now, but we're planning to make the doorway 7 feet tall.
7 feet tall, okay.
And then we're gonna have it secured through zippers. It's not gonna be airtight since the negative pressure allows for it to have air go in. And in terms of the width, it's going to be 6 feet wide, but we can change it so this can be we can unfold this way if we need to like slide in like a big machine or gurney or a hospital bed.
Thank you.
What are those panels, like the big clear panels, made of again?
It is made out of linear low density polyethylene, and it is it's plastic bag like material but much tougher.
Okay, so the panels below it all fold up to be really compact, but do those top panels get compact in any way?
So these rods right here, I forgot to mention, they can retract down here. We're gonna have retractable rods that can retract into these little divots right here. And that allows the roof to be lowered and allows for the compact design or compact folded up, for it to be compact and folded up.
Interesting.
Hey guys, really nice job on your CAD and sort of just walking us through the dimensions and calculations that you did. So since we're looking at this right now, I had a question about, can you walk us through the steps from, let's say, you need to use one of these. Do you find a space, you sort of deploy it, get it all set up, and then roll the, I guess, yeah, maybe I'll stop there. Can you just walk us through from how you get the patient in there and how you set this up?
So first you find a space that obviously you can set this up in. And then first, you want to set up these little filters. So you need the input and output. And then these cost around 1,000 each, but they can be used. So they're set up, and then we get this thing which is which is folded up. You start unfolding it out, and then you open this doorway up, and then you can roll in patients. You can roll in the patient, you can roll in the materials, you can put in medical devices.
Sorry, and I'm sorry if you just answered this question. How tall is that, I guess, the doorway? I feel like you just answered this. I'm sorry.
7 feet.
Oh, got it. So just that bottom part is 7 feet?
Oh, the door, or oh no, this 7 feet. We weren't able to CAD the doorway into the plastic right here, but
oh, got it.
Planning for it to be 7 feet.
I see. Got it. Thank you.
Sorry about that.
So how many people do you guys think it would take to set up one of these? Like, I don't think you've done like testing on it, but just like theoretically, how many people, maybe about how long?
Probably like maybe 3 or around 3. The panel is around 30 pounds. So it definitely can't be a one-person job. But however, unfolding it shouldn't be too bad.
I have a question for you guys. First of all, I wanted to say, really cool idea. I like how it can have the negative or positive pressure depending on what you're using it for. So my question is about the water, and I have a couple of questions about the water. One, I was wondering, where are you getting your water from to fill this? Does it come, with the water already in it? Do you fill it up once it gets there? Two, I guess, how would you take the water out if you're going to move it? Or have you guys thought about that? And then I guess, what happens if the water leaks out? Or is there a possibility that the water could leak out?
So with these panels, they're all hollow. And then there's a hole where you can place or fill it up with water, and preferably you'll only fill it up with water if you're outside when it's exposed to like wind and stuff like that. So the water allows it to be weighed down. And then there also is like a hole on the bottom where you can empty it out and the water can go out. But the problem is that it's going to be just like everywhere. So that's another thing that we're trying to think of like a solution for.
Sure.
And we'll only fill up the panels that aren't the door and the ones without the electricity, because that's kind of interesting.
Okay, got it. So you'd fill it up, take it out. Is there any possibility that it would leak, or is there like something that you guys made within the panels that you're pretty sure that it won't leak? Say if you're, I'm just thinking of like, think about a water mattress, I guess. You know how sometimes it leaks for people? I was just wondering if you guys had thought of that.
The only way it would leak is if there's damage to the panels itself and it like creates a hole. But other than that, the plastic is all, non-porous, so it shouldn't be leaking.
Okay.
Hey guys, it's Anthony again. One more question, kind of the thought process of like an end-to-end solution. So if we take an example of a high density population area where space is limited, such as, let's say, New York, where would you imagine this would physically be deployed?
Well, in New York, I know that they have like, there's like a few warehouses. They tried opening up a warehouse place, a stadium that has like, it's like filled with like hospital beds for COVID patient. And I would imagine that could be in like a huge warehouse, like in there, or like you can go to like this building that's already being used and you clear it out, and then you can deploy these rooms inside the warehouse or the stadium and just line it up, like sort of like how cubicles are in an office.
Cool, thanks.
Okay, do we have, one more
sorry,
question?
one more question. Who would be the end, or who would be the buyers of this?
Maybe perhaps the government could have some use for it. You know, like the military we know have been deployed to try to, at least they were in mid-April, and like New York, for example, to try to like contain coronavirus. Hospitals, maybe FEMA, disaster relief. Just those are some examples.
Okay, cool, thanks.
Hey guys, very nice CAD. I'm thoroughly impressed with it.
Yeah.
I do have one tiny question. So your linear low density polyethylene, is it see-through? Because would there be a situation at which you need to look into and look at your patient but not be able to see the patient? Like, is it opaque enough where you can't see through it, or you can kind of see through it? Do you guys know this, or?
It can be as opaque as you want, so it can be white, so you can't even see through it, or it can be as clear as this, so you can see through it. So we can make, like, for example, these walls opaque, so no one can see, but like this wall right here to be clear, so if the nurse is stationed in front of it, then they can look through, but anyone like behind it can't really see through it.
That's cool. I like that.
Awesome, thank you.
Any more questions? Are we good? Okay, that was a great presentation. Thank you, Team 3. That was really cool. So Team 1, I'm not sure who's sharing your presentation, but whoever is going to should do it now.
Yeah, just 1 second.
Okay. And then while we're in this intermission, can someone from each team email me your PowerPoint and or screenshots of CAD? Thank you.
All right, should we get started?
Yes.
All right, so hello, we are Team 1, and first and foremost, we would like to thank all of you for taking the time out of your day to listen to our pitch. Slide. So the main problem that we want to address is obviously the COVID-19 pandemic, right? With quarantine having been going on for so long and the uncertainty with how much longer it's gonna go for, there's a lot of concern regarding the economy and how much it's gonna recess. And so a lot of people are calling for the reopening of businesses and schools. On the other hand, there are a lot of people who are very anxious and worried about what would happen. Many are calling it the second wave of coronavirus infections. And so what we would like to do is present a solution to that problem so that we can ease the public unease and reopen schools and businesses. Slide. So as UC Davis students and as people who really want fall quarter to be on campus rather than online, our main audience would be the students and faculty of UC Davis, just so that we can mitigate the spread within the population of UC Davis. But if manufacturing can get large enough, we would like to expand our audience to delivery workers, custodians, healthcare workers, food workers, and really just anyone else, because everyone is susceptible to this disease, not only those of old age or of or those that have other conditions. Slide.
And so our product is called the Mindex, and what it is, it's a portable and multi-use tool that reduces the contact of everyday applications. So it would be used to help open doors and push any buttons that you have when you're in public spaces. And so as you can see in the picture right there, it is like a keychain, like a touchable keychain that helps you just do things with your everyday life. So next slide. So these are just some illustrations of how they work. So the two prongs on the device would latch onto the handles and would help you turn. And there's a nub on the end that helps you push buttons, such as like when you're using the elevator. And it's also very light and small, so you can fit inside your pocket or attach to your keychains. Next slide. And so some other features is that the dimensions are, it's about 1/2 inch thick, 1.5 inch tall, and around 4 inches wide, or 4 inches long. And we also, this is depending on how, what materials we're going to use, but it would be 2 colors, which helps the user differentiate from what you could touch and what you can't touch. And so at the end of the day, we also want it to be microwavable and dishwasher friendly, just for those who do want to like zap the bacteria away if they feel like they can. And it's also, again, attachable to a keychain and can also act as a box opener because the edges would be sharp enough.
Hi, so I'll be going over the materials in the manufacturing. So we specifically designed this product keeping in ease of manufacturing in mind and like practicality when it comes to use, manufacturing, and cost. So the main way we would like to manufacture this product is through laser cutting. So we research different materials that are one available in like the team lab and are strong and cheap. So the 2 materials that we came up with are Delrin and acrylic. During fall quarter when I did my PME project, Delrin was a material that we specifically used because of how cheap it is and because of how strong it is. So laser cutting is a very cheap and fast process. So we can so because the product is essentially just a piece of plastic, we could produce one in like around 20 seconds. So both these materials are dishwasher safe, but only Delrin is microwave safe. They're both strong and sturdy, and we estimate the average cost per unit to be $1.31. Of course, this is just an estimate, and like the actual price may vary. So next slide. So because of the nature of the project, we realized there are more than one way to manufacture a project of this sort. So obviously, though, because of how cheap and fast laser cutting is, that's like the main way we want to do it. But 3D printing could also be an option. So the benefit of 3D printing is we customize the product as much as we want. So with laser cutting, because as the sheets of plastic come in specific sizes, here we can make it as thin or thick as we want, and we could also have the 2 colors idea where we could have one side of the product be a different color and one side a different color, so the person knows what to touch and what not to touch. So next slide, please. So again, just like with laser cutting, we have 2 different materials that we can potentially use for 3D print. That's ABS and polycarbonate. Polycarbonate being, ABS being the cheaper but not as reliable version. So this is not microwave safe, but and it's not as strong as polycarbonate. Slide. So we also realized that this product could be used with a host of different accessories. For example, the keychain that most students in UC Davis already use to put their ID cards or their bike keys. This could simply latch onto that, and they could use it whenever they wanted to open doors and so things like the DC and so on. And also, we try to incorporate the product, like the function of opening a doorknob, which is something the product can't do on its own. So if it's paired with a plastic attachment to the doorknob like this, then it could be used instead of a finger to open a doorknob. Next slide. So yeah, so because of this, we believe the main features of this product is that it's very simple way to mitigate the spread of diseases like COVID-19, and because of its low production costs and ease of use, anyone can use it at any time, and it can be used, and things like availability won't be a problem. Next slide. Thank you.
When you showed the image of them using the tool to open up the door handle, it kind of looked like to me that it could slip off the door handle. Did you have like a thought process to preventing it from slipping, or were you anticipating like it catching that hook on the end of the door handle and not slipping? And then like, how difficult would it be to open the door with that? And then
So
hold
Yeah,
it?
so can we go back to the slide with the, it should say other features for Namrata.
Yeah, 1 second. This one?
It should be the slide 7. Yeah, so as you can see on the second prong, the one closer to your finger, it kind of, it's thinner and gets thicker. So our whole idea of that is that when it attaches to the doorknob, it would be easy to use it for different widths. And so as you go more in, it would be more tight and it would cling onto the doorknob.
Oh, that's clever. Okay.
This is Anthony. I'll jump in. I might have to give you guys some tough love. I imagine this would take you about an hour to manufacture. Do you guys have a working prototype?
No, we don't have one right now, but because like we don't have access to 3D printers or laser cutting. But can you elaborate on why you think it would take so long?
I think it would take you guys about an hour to take a piece of any type of cutting blade, perhaps, or a hacksaw and some plastic and kind of make that out. The other question I had for manufacturing is, have you guys heard of injection molding?
Yes.
Could you comment on why you didn't decide to go with injection molding?
Basically, we were only exposed to like what we know that's available in the team lab, because that's like what I've seen. That's what people, those of us who did BME have seen. So that's what we know is there. So that's why we thought it'd be convenient to just use what's already there on campus.
Also, just to add on, we thought that laser cutting wouldn't be taking that long, because when we did our project in fall, we made like a device, and it was like kind of like a bigger size than this, but it took like 5 minutes to laser cut. So 3D printing would take much longer, but laser cutting was a short period of time.
Yeah.
Okay, my last comment would be, if I had to guess, to injection mold this thing about volume, it's probably a few pennies per object. You could probably injection mold multiple per minute, probably in the tens per minute, just as a heads up, guys.
All right, thank you.
First off, I do like the visuals. I like how you guys added all those cool pictures and everything. I would just like to say, a lot of people don't know about this, but Steven does have a small injection molding capabilities. He doesn't really talk about it very often, but he does have that capability, just so you guys know, future reference. I do have one question. So you guys, have you guys decided on a material yet, or are you guys still up in the air about it? What's your guys' thought process on materials? Because you guys mentioned 3 of them, but it never really seemed like you guys concluded on any particular one.
So what we decided to do was we decided to have options for the materials, not to fix one right now, because we don't know we can never know what will work best unless we actually make a prototype. So we have 4 options, and we think one of the best features of a product is how it's so easy to manufacture, and it has so many options on how to manufacture it. There's 2 different methods and 4 different materials. So yeah, that we kept that in mind and made sure there were a lot of options.
Okay.
Yeah, we also thought we should probably make them and see which one works best on a door, as he said, and then make more of that. And since now we don't have access to any of these, we wouldn't really know how thick or how durable the materials are.
And then I guess something else that comes to mind. So you guys showed a lot of the turn handles, but in my memory, we have a lot of more door handles that are more vertical. And those vertical ones tend to be on the little bit thicker side. Is that a concern for your guys' design? Because if I remember correctly, your design, especially your slot, is on the smaller side. Is that a concern you guys have, or did you design it where it would be just enough to fit the vertical handles as well?
Yeah, I think it would be just enough to fit the vertical handles. because we made sure that it'll be good, like it can be used for as many different scenarios as possible. And also, like, if by chance our current dimensions isn't like comfortable to use or doesn't fit, we can always change that to make sure. We can make it bigger or smaller depending on how well it works or doesn't work.
Okay. Thank you so much.
Hey guys, so really nice job coming up with sort of just this portable option to minimize contact with these sort of high touch surfaces. So I like that. I guess I'm wondering if you've thought about how you would potentially, let's say, disinfect the device between uses, because I imagine, you know, once you've touched one surface, I guess the goal is you wouldn't want to spread germs to another surface. And also if they're on your keys, you may stick them in your bag and throw them in your car. I guess that's my first question. And then the other question is sort of related to how it actually interacts with, let's say, door handles. I guess going off of what Thomas was saying, have you guys thought of maybe having a modular component or maybe even an adjustable part where you can accommodate different doorknobs? It's just sort of one idea. And then my last sort of thought on that is, do you have an idea of the mechanical strength that's necessary from your material in order to be able to open doors? Sorry, that was a lot in one statement.
So to answer the disinfecting questions, that's why we tried to make sure the materials are microwave safe and dishwasher safe. So someone could just put it in the microwave or put it in the dishwasher to clean it. So the next time you go out, it'll be, it's clean. And for the touch part, that's why we wanted to have two different colors on the product. So one side is blue, one side is red. The person knows not to touch the red part and to only keep the hands on the blue part. And but mechanical strength, that's why. So the reason we made it so thick, like thicker than like probably twice as thick as some phones, is because plastic won't be as strong as something like metal, but it'll be cheaper. That's why we made it so thick. So like make sure there's enough mechanical strength to like turn, like to open a doorknob or turn a door handle. So, yeah.
Awesome. Thanks so much.
Thank you.
Okay. Any more questions? Okay, that was great. Wow. All three teams did an awesome job. I kind of followed all of your projects, but I tried not to look at them the past couple weeks. And you guys really like developed across this time period from like the first things that I saw of everyone's team and then what was presented today. You guys all really like, I could tell that you all talked to each other and you talked to other people and you looked at how things were going to work and then you reiterated, and it looks really cool. You guys came up with really great stuff. So if all of the team members want to head out, go get dinner, relax, your weekend starts now. Me and the judges are going to deliberate for hopefully not too long. You guys did great presentations, so we really just have to pull up some numbers. And then I'll get back to you guys Monday.